Okay. So, who here is interested in making things go fast? All right. That's terrific. So, in this talk, we're going to talk about a few things I learned while during my 6-year stint at Facebook. I worked as a research scientist, which really means you're like glorified, as Venkat said, software archaeologist working on things. And I've made a few small discoveries in terms of optimization that I find very interesting and I wanted to share with you all. One of which is what I call the forgotten parallelism. So there is a lot of talk about like parallel software and all these great systems and fork join and what have you, and work stealing, all of these great things. There is a form of parallelism that doesn't require you to kind of start threads or distribute processes and do these awesome things. It actually requires you to write code in a odd, specific way. Who has a guess on what that could be? The forgotten parallelism. Everybody forgot about it, apparently, right? So let me show you, is it visible? Yeah, quite so. Let me show you, this is the Intel Halem architecture. And I don't have like a point or anything, and I don't want to favor any side over the other. Okay, there's like 2 more people on that side, so I'm going to be there. You guys, so this is like the traditional representation of a CPU, and it's actually not a CPU, it's 1 core in a CPU. So you have like 8 of those, right? So the data flow, the instructions flow top down, and there's essentially like the whole pink part, the color of like vomit after a night of vodka. That would be the decoding of instructions. So it transforms the complex input instructions into nice RISC instructions that are simple but very large. So there's like a 128-byte width here. And then we have something interesting because we get into like where the action goes. And here's where the action goes. That's called the... Come on, you guys. You can't be that high level. You gotta level with me here. Hey, thank you, Hubert. I love Hubert's voice. He has like so much. Actually, you should voice over my talk. So this is the ALU, Arithmetic Logic Unit. And what's interesting about this ALU is there's a lot of stuff that's not vertical, it's horizontal. And remember I said instructions flow downwards? So at this point, there is a fork in the road, and as the saying goes, you should take it, right? So at this point, we have several things potentially happening literally simultaneously. There's a stored data, there's address calculation, there's integer, add, move, whatever, floating point, add, and move. And you can count on things like you can have an integral operation and a couple of floating point operations happening literally simultaneously. And the interesting thing is you don't do anything about it. Anyhow, so at the end of this, this is actually a programmer helper because it's octuple associative data cache, whatever. Oh, sorry. This is the program helper, memory order buffer, which makes things that are happening weirdly in parallel look relatively tame to you as a programmer, so you don't have you have the right sequence of operations, almost real. Okay, so the action is parallel. And the question is, how do you expose that parallelism? How do you make these good use of this little parallelism? And the interesting thing is people, like once you lose that, you never gain it back, right? So to kind of ever gain it back, you gotta buy more computers. So you underuse them as well. You see my point? So there's this whole, there's this whole talking about the dark silicon. Dark silicon? Like we have so much processing power, so this ALU has so much stuff on it, so many transistors that can do interesting stuff. Interesting to some, right? Not everybody cares. But, interesting stuff. But we can't bring data fast enough into those transistors to make them do the interesting stuff. So then how do we use those? And it's very interesting that this instruction level parallelism happens even before we think about it. Because there's a whole cabal, there's a whole conspiracy, friends, that is at work making our code, our serial code that is, parallel. There's all of this laundry list of things and many others. They only conspire together to expose parallelism in serial code. And if you sit down and write serial code, it's going to have an inherent parallelism. And there's a magical number, which is like across a large variety of coding styles and applications. Is going to be, actually, this is the amount of parallelism in serial code. Who knows what that number is? How parallel do you think you're writing code today, on average? Like, 1.5? Like, you write code that's serial, but it's actually 1.5 parallel. Good? Who gives more? 2? Is your code two-way parallel without, yes, who gives more? This is a kind of a, yes, come on, I should have that fast voice of like folks who do that kind of stuff. So actually it's 4.2. So the average serial code has 4.2 inherent parallelism, which is discoverable and automatically parallelizable. This is the forgotten parallelism. And now what I want to do is discuss ways to expose and exploit more of that parallelism, make it, I don't know, 4.5, because it can happen. Without actually sitting on, you got a fork, and you got to create threads, and you're going to do all these awesome things. No, it's just rewriting code in a slightly different manner. And it's actually not really just slightly, but it's rethinking your code in such a way that's going to make it parallel. So the key to the kingdom is you got to have fewer data dependencies. What is a data dependencies? Probably it's good to know, right? Yes?
Yeah, I mean, this is typically a field filter because you only want a few variables which you loop over, and maybe you take the one value and calculate or multiply that with a lot of different values. So you basically have one that's constant and you loop over, send them all around.
Right, so that was a complicated explanation. Why don't you do what Venkat said, make it simple? What would be a simple explanation? Data, sorry? That looks simpler, but it requires quite a bit more background, the whole hazard thing. What is data dependency? An operation depends on the result of a previous operation, friends. That's it, right? So that was an example given of the simple notion. So whenever you have something that depends on something else, you have serialism, and you have a data dependencies because, whatever you do must wait for the previous operation to end. And that's how the cookie crumbles. So, well, we want to make those, as few as possible. We want to minimize data dependencies. And I'm going to show you an example. Who knows C++? C++, I don't care, C++. Right, okay. Who understands what this function does? For example, like looking at the name. Yeah, it converts ASCII to integer. So it takes a pointer to the beginning of a string of characters and a pointer to the end of the string characters in sort of STL style, if you wish, 2 iterators, if you wish, right? And it's going to compute the conversion of that string of characters to an unsigned integer, so we don't care about sign, kind of simplify our life a bit. And it does so by successively multiplying the current result, the running result, by 10 and adding the least significant digit. Right? The current digit. Now, this function is called actually Horner's scheme. If you crack open any book on algorithms from way back when in college or whatever, or for me it's way back when, for you it may be much more recent, but if you crack open any book on algorithms, you're going to see this is how you do it, and it's been like this for literally the past 50 years. It's considered an algorithm that is classic and at its optimum. And I'm here to tell you this is not, it is classic, but it's not at the optimum. It can be improved radically. The problem with this algorithm being it has too many damn data dependencies. And who can tell us what are some of the dependencies involved? Yes? the result depends on its previous version and also on the current character, like star B, by means of a complex pattern, right? We have the result is result times 10 or times whatever, plus whatever. So that's a problem. And I sat down, the funny story. I was working on a database of high performance, high scale. We're talking petabytes, and it's called Hive. Anybody knows Hive, the Hive database? It's used for offline data at Facebook. And it's a awesome data, it's great. And just because it's so awesome, so powerful, so fast, they decided to make communication between that database and the client computers in the most branded possible text. They said, it's too powerful, actually. Let's make the communication the stupidest format there is. Keep it kind of in a textual format. So then, every client, whenever they need to do something, they're going to do what? Read numbers from the database, convert them to goddamn integers, and floating point numbers and what have you, dates times what, right? And then do some computation, and then convert back to text and send it to the database. I am not kidding. This is not a joke. So we had like these Hive applications, and they're kind of slow. What's happening here? Let's measure this thing. Let's see where the time goes. Guess what? All the time goes here. Right? It's because whatever you do, you're going to have to convert every damn column and every damn number from text, right? So that was a bummer. So, who's the idiot who's going to help us improve this thing? Oh, there's Andrei, right? So here I was working on this. So I spent on this like probably a couple of weeks. Sleepless nights, what have you. It was, remember, if this was a movie, that would be one of those ellipses in the movies where I kind of sit here and kind of think really hard and kind of scratch paper and kind of throw it away and kind of beat my wife. I don't know, that kind of stuff, right? So it was one of those nice sequences in movies like, Rocky Balboa and whatever. So great. And I came with the following great idea. I said, what am I doing here? I'm going to kind of give justice here and kind of stand on this side as well. So I said, let me write this with pen and paper. What is the actual computation that is performed? And I said, okay, so this is what the algorithm really does in inlined math form. I noticed like the first thing I'm doing is like an idiot, I'm multiplying by 0. That's not a good sign. I mean, the sheer fact that you're doing some useless operation to start with is not a good omen, right? Agreed? So then, so 0 times 10, okay, thank you very much, idiot, right? Plus 5, everything times 10. Because it depends on the previous result. Remember the algorithm? So then plus 2, everything times 10, plus 3. Everything times 10 plus, and I can't yell any louder because I'm going to destroy my voice, but essentially, I'm doing something really, really complicated. I mean, I love Venkat because not only because he loaned me the clicker, but he made great points about simplicity. This is not simple. It does not look simple, it looks ugly, it has too many parentheses. And I like Lisp, also has parentheses, but in Lisp, parentheses serve a different purpose. They represent a b-dimensional data structure in a unidimensional string, right? So it's a different, they're grammar separators, if you wish. They are punctuation. In here, they're not punctuation. They are an obstacle to efficiency. Because what does the parenthesis do in math? It forces the order of operation to be not the natural order as whatever deity intended, right? It says, you know what, you shouldn't do things as they are. You shouldn't do things like the path of least resistance. No, you should do this first and then that. Right? So parentheses is already a data dependency. You look at the math, you see it has too many parentheses, there's too many data dependencies. So now, how to improve this thing? The question would be, thoughts, ideas? Yes?
Just expand it so that you multiply with 100.
So we multiply by some constants, and there's another? Yes? Sorry? So use powers of 10, use sort of the positional. Well, I gotta admit, I'm not as smart as you guys. I went through a stage where I was thinking there's gotta be some divide and conquer solution to this. I thought maybe I divide a string in 2 or more pieces, and then I kind of figure out this. And it dawned on me, actually, this is interesting because it leads us here. It gets us here to this nice point in our lives, whereby, this is actually beautiful. And it has no parentheses. And actually, it aligns nicely. So you see the number here is also on the vertical, and we have a triangle here. So, I think Da Vinci would like that, right? That kind of stuff, right? So you're like, actually, I can see how this goes. It's really a simple and nice and shapely, if you wish, formula. And, LaTeX loves this because you can align with LaTeX all these pluses and stuff, has special code for that. So, okay, well, this is pretty awesome. So let's try this thing. And the code looks just a bit more involved, but there's nothing complicated about it because I'm really one thing I really take pride in is I can write powers of 10 real nice. It's there's going to be a triangle here, right? I didn't write everything, right? So there's going to be this nice triangle with 1 followed by 19 zeros, and then 1 followed by 18 zeros, and so on, and all of them are going to nicely converge there. And then we have enforce, by the way, is kind of like an assert that's always in action. So it enforces, like it throws an exception, whatever. So then I say, okay, so I'm starting with the result. And here I'm going to where does this guy come from? 20. You should never have literals in your code, right? You should have only like -1, 0, and 1. And everything else should be a symbolic thing. This comes from there, and it means it's the end of the array. And it positions me, starting from the end of array, it goes back to whatever the most significant digit is. So it's going to position me in this table, in our example, here is going to position me on 100,000, right? So it's going to position me there. So by the way, I'm kind of doing, instead of kind of computing powers of 10 on the fly, I'm just going to put them in a table, just so I save a bit of work. But that's not instrumental. So I'm starting with this I at sort of the right position of the most significant digit, power of 10. And then I'm going to say, okay, so let me kind of go from there. And result is result plus power of 10 of I++ times the current digit. And that actually implements that very simple algorithm. So it's just a different take. But it has fewer data dependencies, because now result still depends on its previous value, but only by means of a plus. And guess what? Plus has an interesting property, which is called, it's commutative. And it's interesting, but probably not for this case. Associativity. The interesting thing about plus is it's associative, which means pluses can be done in any order, including in parallel. And guess what? The CPU architects know that. Whenever they see a repeated addition, they're going to be like, yes, you're on, buddy. This is awesome. I know what to do here. Whereas in the previous algorithm, it's a much more complicated pattern. So I've got to multiply that with 10 and kind of still do this and have a coffee and that kind of stuff. So it was very different. And this approach is going to be perhaps faster. So what do you do to make sure to validate the fact that it's faster or not? Measure. I've seen so many people too smart to measure. And, it includes me as of like, a while ago, like a week ago, right? So, when you measure, you actually get a leg up on experts who are too smart to measure. So it's really good, right? So let's measure this. Well, I did, and my question to you is like, how much do you speculate we're going to win here? We're going to win 10%, 20%, 50%? 80%. Thank you. Who gives more? 200%. So the 3 times faster? All right. Thoughts? Depends on the length, yes. So we got to measure for all number lengths. Yes? 5 times. 5%. All right? And it could be slower, by the way. So it does happen. It did happen to me with disquieting frequency that I thought something's going to be faster. It was a net pessimization, right? I spent time actually making things slower, which was pretty, just not counterproductive. So it's actually, that gentleman was right. It's 3 times faster, and it trails down to 2 times faster. And what I like about this graph, so this is the relative improvement on the baseline. By the way, so I make this, so I just had this class which, due to which my voice is so coarse right now, and also my accent. I didn't have an accent when I came here. You should know. I had a perfect British accent. It was awesome. And just because I'm so tired, it's just... So the nice thing about this, first of all, let me take a parenthesis and tell you about baselines. What's a baseline? A baseline. Yes, in a measurement. What you're measuring against. I've seen too many people who don't use baselines. And it's funny because it sort of makes a bit of a difference between a newbie engineer, if you wish, and a scientist. Because scientists always use baselines. And also, marketing people use baselines. In marketing, you always choose the worst baseline you can find. Right? So you look good. So I'm going to choose this shitty algorithm, this crap implementation, this awful product. And then we're so much better than this, the leading competitor, and that kind of stuff, right? So marketing people do that all the time. But as a scientist, you want to choose the best baseline you can find, because that means progress. If you're better than the best, then it means global progress in humankind, if you wish. So that's why you should always use baselines. And if I showed you here nanoseconds and microseconds, you should punch me right now, right? Because this takes 15 nanoseconds to do this operation. You're you know what? I have no idea what you mean with nanoseconds. Maybe the baseline will be faster. Maybe the old way would be faster by a few nanoseconds or whatever, microseconds. So I should show you by how much the current proposed solution improves over the baseline, which means 1 is just the same, and below 1 is not good, and above 1 is interesting. That's good, right? So parentheses closed. Use baselines, people. Whenever you do performance, use baselines and measure, right? I hope I'm preaching to the choir here. So we are at 3.4 trailing down to 2, and that's a very nice result. And actually, there's one more thing that I like about this algorithm is that it is better for small numbers. The improvement is even so much better for little numbers. And there's the laws of big numbers. The law of big numbers in math, right? They say those with growth. But actually, in programming, there's the law of small numbers. Most numbers are small. If you look at all numbers in all applications in this world right now, most of them are about 7. And, no greater than 42, that kind of stuff, right? Most strings are empty, and those that are not empty have 1 character. That kind of stuff. Most things are going to be small. Of course, there's going to be a lot of large numbers as well, but how often did you have an array that had a size of 19 bits there, right? Maybe not too often. That kind of stuff. So I like that the improvement is so much better for small numbers, because it turns out that for small numbers are much more frequent. However, there would be exceptions. Who can give us an example of a number that is actually shouldn't never be small? An integer, 64-bit. A SHA, the hash ID, user ID, a random generator number. Anything that is supposed to have high entropy would need to occupy all the bits in the 64-bit integer. So if it's small, that's a problem, right? So by the way, Facebook started with. It's funny how things start, right? So you start Zuck has ID 4. No joke, his ID on Facebook is 4. And the first 3 are not occupied. Right? 0 to 3 are not taken. I tried, but no, they wouldn't give it, right? So Zaki is 4, and then it kind of grew like by 1 after that, and it was kind of weird. And then they started generating, like when they got like to 10,000 people, like, whoa, we're doing it wrong, dude. Let's ascribe these random IDs. Great. So associative means parallelizable. There's a deep truth here. Whenever you have an operation that's associative, you're in good shape because you can parallelize it and the CPU can parallelize it for you. So now let's apply an optimization known as strength reduction. Anyone who wrote knows this? It's kind of a compiler term, compiler architecture term. Hubert, talk to me. Right, so strength is a bit of a misnomer. It's kind of expense reduction, which makes a lot of sense. Economy, friends, right? Strength reduction means you take a multiplication and replace it with an addition. That kind of stuff, right? Or you take a power and you replace it with a multiplication, or you take an addition and replace the addition with absolutely nothing, because there's nothing cheaper than addition. Any addition is like 1 cycle, right? So let's focus on this thing, which is enforce, which like assert, like verify that the input is correct. So you gotta have it. Make sure that the current digit is valid between 0 and 9 ASCII, right? So actually, if after inlining and whatever, it doesn't really matter, it reduces to if the digit is less than 0 or greater than 9, then I'm gonna throw something as the incorrect input. And then we have the core loop in the computation. And the question is, let's improve on this a bit. So let's take this operation here and make it just a bit faster. Because let me point this out to you. This is like short circuit, right? Short circuit evaluation. A great invention in the early days, but right now it's actually bad because it introduces a dependency, right? Because in order to even evaluate this expression, this comparison, this must be finished. So what do you do as a good engineer to make sure that this is not a dependency? Remove the dependency for me, please. Sorry? Use and. And is the same deal. It's just it's or and and both are short circuit. Logical or, logical and. Sorry? Okay. Other thoughts? Yes. Sorry?
The second if condition of the second part.
The second if?
Just split it up into 2 ifs.
Split it up into 2 ifs, but we still have the same dependency. It's serial. If this guy and then I test that guy, I want to, let me clarify what I want. Remember that nice ALU with things that it can do in parallel. This and this can be done in parallel. I want them done in parallel. Yes. Use a bitwise OR. Lose one pipe here. Lose one pipe. Thank you. Lose one pipe. And the bitwise OR is going to give me the same result as the serial OR, but it's going to allow parallel execution. Which do you think is faster? So this guy or that guy? Do you think it's measurable, first of all? Do you think I can measure difference? And if so, which is going to be faster in your intuition? The second is going to be faster. So I thought in my recklessness. Yes?
Are you testing on this when you are doing the measurement? Are you testing on every possible string? Or are you testing
No, I'm testing on every possible string length, random numbers. So random numbers of length 1. Sorry?
only numbers?
Yes. But this is the thing. I don't want this to be fast, because by the time you throw, you can pretty much the performance is down the drain. I'm testing on valid input. I want the cost on the normal path to be as low as possible. That's a good point. Thank you. I'm not measuring the speed of exceptions, of errors. I care about the speed in the normal case. So here's the interesting part. So I measured this, my baseline. I measured this, and they did just as fast. So I was like, oh, so there's no difference here. But I looked at the generated code, and GCC generated the same code for both. GCC was way ahead of me. He said, oh, that guy thinks he's smart. So I'll show him, right? So the code generator is literally the same. The compiler detected that what I'm doing and figured out how to parallelize things way ahead of me thinking about it. But, you know, I'm not one to give up without a fight. So I said, how about a table lookup? How about the table? You know, isDigit looks up a table of 256 bytes and kind of, it goes in a table, and the table has bits set and that kind of stuff. So it's a table lookup isDigit. Which do you think is faster, this guy or that guy? Thoughts? IsDigit versus an operation. So tables versus computation. Thoughts, ideas? Yes, hypotheses. You think table is slower? Who else thinks different or the same? Table is slower, table is slower, table is slower. Actually, it's just the same. GCC generates the same code for this guy too. I was shocked that GCC was smart enough to figure out, maybe it has memory, maybe it figured out all my experiments. It said, let me show this guy what an idiot he is. And it said, you know, in your face. So, am I sure I'm compiling different code? Yes. So it generates the same code, even though ostensibly it's a table lookup and a kind of a function call into a library and stuff. And GCC apparently knew about the semantics of isDigit and said, oh, I know what this idiot is trying to do, so let me do it the fast way for him. But of course, I wouldn't give up. And I tried something more principled, which was let me use unsigned arithmetic and modular subtraction. So, you know, the way I went was the following. Let me convert the digit to an unsigned number, 32-bit. And then subtract the 0. And the nice thing about unsigned numbers is they can be negative. So whenever I have this the subtraction, it can be between 0 and 9, or something larger than 9. And everything that's larger than 9 should be wrong, right? Everything that's in between is good. Whatever would be negative in assigned arithmetic would go somewhere weird, somewhere in the wrong range, right? So that was my reasoning. And I had to prove myself that this is correct. Because the fear would be, what if by some arithmetic property or whatever, this subtraction of that would be negative and whatever goes by mistake into the right range between 0 and 9. So who can actually sketch a proof of what is happening here being correct? It's not quite obvious, right? So I'm sure like experienced engineers, they kind of look at it, they squint a bit, and they're like, oh yeah, that's plausible. That makes sense. Like, that could work. Let me test everything. Let me test it and see if, yeah, I tested it, it works. So that's not like, you know, I'm saying principled approach. I'm not saying like a test everything approach. So the principled approach says this. Well, if I had a number that, you know, a negative number converting to the sort of the false positive number, the false right number, then I would have two values in the kind of domain of the minus operator in unsigned numbers mapped to the same number, right? I would have these two, you know, a good value and a wrong value both mapped to the good value. So actually, that can't happen because minus is what they call a modular subtraction. And when you do modular subtraction, it has a property which is an arithmetic property called it's bijective, but you know, there's one of these I'm interested in. Bijective means injective and surjective. Surjective means it covers the whole space of the code domain. And injective, which is where we're going to, means an injective function. An injective function, also known as an injection, or a vaccine, colloquially, right? That was a joke. It didn't really work out, right? So, yes. Right, exactly. So an injective function has exactly the property you're looking for, which it always maps distincts to distincts. It never maps two distinct inputs to the same output. So then we use this mathematical fact to say, actually, I don't even care what happens because I know if I convert the right inputs, you know, the right digits in ASCII to the right digits in the range 0, 9, whatever wrong digit I have, they're going to go elsewhere. So with one test, I'm done. And even better, I reuse this subtraction here. I just save it in a variable, and I'm reusing it here. So I actually saved one subtraction too, right? So is this going to be faster or not? Is GCC going to still ruin our day? Is it even, okay, let's say it is different. So GCC didn't do this, well, naturally. So I had, the code generator is different. The question is it measurably faster? Is it going to make an impact on our business? It turns out it's faster. Significantly. So this plot shows ILP is our ILP version. It's not the initial baseline. So baseline is at 1. So this would be the baseline. And we have the ILP in this nice violet color, and we have ILP plus unsigned in green. So we see that the advantage of ILP plus unsigned is going to get better with the number of digits. Why do you think so? So why does this gap increase with the size of the number? Let's look at the code again just for a second. This is the core loop. Well, folks, so the reasoning is I'm saving a little for each pass through the loop. So the more the loop goes, the more I'm saving. So that would be the obvious explanation. So we have a nice trend here. And sorry? What is the bump? Yeah, what is the bump around 10? Right, is that? What's the bump around 10? I'll tell you, I have absolutely no freaking idea. I'm not kidding. So actually, it's visible here too in this plot as well, where I kind of replace it with a drawing. And it's just the fact of computing. When you optimize, sometimes there's artifacts. There's absolutely no explanation you can find, except if a good attendee gives them to you.
I don't have an explanation. But I'm just wondering, your subtraction or your unsigned code is slower for the very small case. So by the law of very small numbers, your code might actually be slower in production because most of the numbers.
So yeah. So actually, thank you. So actually, we can see it's a tad slower for very small numbers, up to 2 digits, 3, 2 or 3. For up like 2 digits, it breaks even. For 1-digit numbers, you're right. And actually, it's a good point. I suppose that the loss in efficiency for very small numbers is not going to be huge. So I'm going to keep this the green version. So just for kicks, let me add a couple of more baselines. So this here at 1 would be A2UL in the C standard library. This is sort of the absolute baseline. You take the library function and just look at it. And then we have our, in yellow, we have our handwritten version, which we showed in the beginning. And we have an awesome baseline here. This is really good to beat. This is Boost Lexical Cast. Why is it so slow? I know Hubert knows. So what does Boost Lexical? It does the same thing, but it does pretty much what Venkat said. It converts everything to XML, and then back. So pretty much, almost literally, it's that what it does. Because what this brain dead function does is it writes the string to a string stream, and then it reads it back as an integer. That code got written. And can you believe it? This is amazing. So I want to convert a number to an int. So let me do the most general thing. I could be anywhere in the world and call it right now, right? Let me do the most general thing possible, which means I'm going to write this to a completely generic stream, and I'm going to read it from that complete generic stream. So I got word that, I gave this talk a couple of times. So I think the Boost folks did get the memo, and I think they improved that function. Is that true? So, I recall somebody mentioned, I didn't verify yet, but somebody mentioned that actually they got the memo and they improved that function. Anyhow, if you're in marketing, you should use that baseline, right? And you're going to be awesome. Great. So let's do one more optimization. And when I say think outside the loop, an obvious optimization that's a classic comes to mind, which would be think outside the loop. Yes? Thank you. Unrolling. So let's unroll this beast. And it gets quite a bit bulkier, but it's going to be a bit faster. So we're going to unroll the loop 4 ways. Why 4 ways and not 3, 5, or 8? Why do you think 4 is it's a good number?
Because you're a computer scientist.
Because we are computer scientists and we like small powers of 2. But there's a simpler reason. I measured everything, and actually the 4 is the sweet spot. This should be the ultimate answer to, you know what, I measure with 3, 5, and 8 and whatever, and 4 would be simply the better performance. There's nothing really interesting about this function. At this point, it got from sort of the ivory tower of math. It got down to the greasy hands of a working programmer, right? So it turns out that it's better, but you see the point stands that it still does a bit worse for small integers. Why do you think it's not as fast for small integers with the unrolling? We don't do unnecessary work. It's all necessary. Oh, yeah, you're right. By the way, this is not the whole code. If you look at, I'm really sorry for I hate this room. It should be like I don't know. I'm feeling bad about those people, and when I'm there, I feel bad about these people. The grass is always greener, right? So this loop goes in 4 steps. But it's incomplete because if you have a number that's less than 3 digits, you're going to have to kind of fall back through the loop and have some fix-up code, they call, that's going to do the last iterations. So actually, it's kind of a bit awkward for really small numbers because you fall back to the previous algorithm without much improvement. So that's the reason why small numbers are not as good. What you can do, actually, is combine the algorithms and say, if it has less than 3 digits, do that, otherwise do that. At any rate, this is kind of interesting. So checkpoint depends on who you ask. Depending on who you ask, love or money makes the world go round. I leave that to your philosophy professor. In algorithms, it's math that make them go round. So many people believe optimization is this kind of weird thing whereby, oh, he's doing assembler. Machine code, he's a badass. No, actually it's math. It's high school and college level math. That's not even super complicated most of the time. But that motivates the transformations that you can do to reduce data dependencies and to reduce the strength of operations used, right? And that's how it works. Exploit instruction level parallelism by keeping those ALUs busy. Spread work around to minimize data dependencies. The code I just showed is part of a nice Facebook library, which is on GitHub, to which I contributed a fair amount. And it has high-performance routines for this kind of stuff. So that is not, however, a strong enough result to be publishable, which is going to segue into a future talk of mine, which does feature a publishable result. With this, I'm going to thank you very much for being here. You've been great. Awesome. Thank you. Thanks.